All right, I'm back for 5.3, ocean and atmospheric interaction. A lot of information to cover in this one, so I'm going to try to move through it pretty quickly. Just remember that you can pause me if you need to try to write down the important stuff. Focus on the things that are in bold. Even then, again, it's a lot to write today, so feel free to try to find ways to abbreviate and shorten the information. All right, let's go ahead and get to it. So, interaction between ocean and the atmosphere. The ocean and the atmosphere interact over long and short time scales. They can work both ways, and they influence Earth's climate and weather. Up until recently, you're not writing any of this down yet, but up until recently, climate changes have happened throughout the history of Earth, but they have been caused by natural deviations from normal processes like solar activity, the change to Earth's wobble, or its kind of tilt on its axis, and the shifting of continental plates. These things can all have an impact on climate and have caused climate changes. There is now another cause for climate change. You'll be learning about that as we go, more so in our next lesson, not this one. All right, so now we're writing for our first part of the 5.3 page of the study guide. Water is particularly good at storing and transporting heat because of that high heat capacity. Remember that term back from Unit 3, that water has a very high heat capacity or ability to hold heat. Now we're writing the warm currents on the western sides of these gyres carry vast amounts of solar heat from the equator up to higher latitudes. So cold currents flow in the opposite direction, and they then come down on the eastern side. So you have warm currents coming up on the western side, and then colder currents coming down on the eastern side. Get an image of this here. A couple of our large gyres doing their job. Here the Gulf Stream coming up the coast of Florida, carrying warm water from the equator, and then it crosses the Atlantic and gets cooler as it goes, and then the cold water comes down. You can see on this image, this is going to come up on another slide, but you can see in this image, this warm water that gets carried upward helps keep some of these northern regions more temperate, helps to moderate their climate and keep them from being really, really cold. Places like England here, if you look at its latitude, it's very, very far north. I mean, it's in line with southern Alaska, and yet its temperature is pretty moderate throughout most of the year because of this Gulf Stream, because of this warm current that comes over and helps to keep it warm. So ocean currents act like a giant thermostat, warming the poles, cooling the tropics, regulating the climate of the planet. World's ocean and atmosphere are deeply connected. If you haven't caught that idea yet, that's something that has come up multiple times now. I want to keep moving because we got so much to cover. So regional weather conditions such as wind speed and direction, air temperature, cloud coverage, precipitation, they all alter oceanic conditions. And here's the part that I want you to take a peek at. You're not writing this down, but I want to point it out real quick. So heat is transferred from the ocean water to the atmosphere, creating more mild climates. So like we were talking about with England, that warm water gets sent over. Some of that heat leaves the water, comes into the atmosphere, and creates that more mild climate in places like England, where based on latitude, it should be a little bit colder. All right, we're moving on to our second box on the study guide, oscillations. These are changes in ocean circulation that affect climate in a very predictable cycle. These are long-term cycles that we can see within our weather patterns. We're going to name a couple of them here. The Pacific Decadal. We don't need to memorize anything about it, just know the name, but it's an oscillation. Has a cycle of about 10 years, and it influences North America and some of East Asia. So in particular for North America, we're going to be talking for the Pacific Decadal. It's obviously going to be along the Pacific coast. Another one is the North Pacific Gyre. And then the North Atlantic Oscillation. All of these are long-scale, multi-year oscillations. Another one, El Nino, and then the Southern Oscillation, which in a moment we're going to learn are kind of two parts of the same idea. Again, we don't need to memorize anything about them. We're just going to name our oscillations. See an image of how they work a little bit there. Nothing about this image that you need to be too familiar with, so I'm going to keep going. ENSO. This is an abbreviation for El Nino Southern Oscillation. So it's the El Nino EN, SO, Southern Oscillation, combining the two together. Scientists use the term to signify that El Nino and the Southern Oscillation are two aspects of the same global phenomenon. Scientists analyzed in 1982 to 83 the El Nino event as well as milder events in later years. They were analyzing them in order to predict what would occur in future El Nino events. And their predictions turned out to be true, that they could use some of these patterns to predict in the next end of the cycle how some of these weather events were going to look. Again, a fair amount to cover here, so I don't want to go into a ton of detail here, but an El Nino begins to form when the atmosphere seesaw. Southern Oscillation brings lower than usual pressure. Trade winds get weaker, coastal upwelling along South America. A little bit more that I want to talk about on the next slide, so I'm going to keep going. Actually, I do want to talk about the second bullet point there. So the interrupted upwelling, this upwelling of cool water from below that usually happens, that the lack of upwelling causes failure in fisheries. This cold water that's not coming up, it's not coming up with all the nutrients that it usually rises up with, means that seawater near the coast is warmer than usual. That may not sound like a bad thing, but it is a bad thing in terms of the nutrients in the water, and then therefore all of the life that can possibly live in that area. So the life in those areas, it gets decimated for that time period of warmer waters. In non-El Nino years, the trade winds push a mass of very warm water, and the Pacific Warm Pool, it pushes it along. But when the trade winds slack off during the El Nino, then that warm pool moves eastward and it warms the coast of South America. So South America is where El Nino really has the greatest impact. And we're going to talk about a little bit about what that negative impact is. Beyond just the fisheries, there are a couple of other things that happen here. So because of this increased evaporation, all this other stuff going on, El Nino brings, it's a lot of rainfall that happens with El Nino off the coast of South America and then on into Southern California as well. But this is the big thing that I want to point out here. So El Nino produces weather events all over the world, but particularly in South America, places like Chile. Some of these secondary effects include increases in mosquito-borne diseases. We think, okay, well, warm water, gonna kill some of these fisheries. Okay, that's kind of a first-hand effect, but a secondary effect, because of these increased temperatures in that region at the time, the water temperatures, the air temperatures, all of it is increased in that area. That's going to be just a perfect storm for mosquito populations and the diseases that they carry. So malaria, encephalitis, dung fever, also good conditions for rodents too. You don't have to write that part down. You see fisheries collapsing, you see wildfires, mass coral bleaching, it's when coral die off, when water temperatures are too warm. Coral are very sensitive to exactly what a water temperature needs to be. So just lots and lots of bad stuff that comes with these with this warming in these areas. All right, I'm going to keep on going and get to our cyclonic storms. All right, so two more squares left: cyclones and the impact of cyclones. So starting off here, cyclonic storms are rotating storms that are generated over the warm waters of the tropics. Always going to be starting in the tropics. They occur over a much shorter time than ENSO does. It's a multi-year period for these cyclonic storms. We're talking about a large storm, but a matter of days or weeks. So tropical cyclones, depending on the region, let's go there. Depending on the region, tropical cyclones might be called hurricanes, cyclones, or typhoons. They're all the same thing, just referred to by different names in different regions of the world. So tropical cyclones are characterized, as you probably know, if we're talking about hurricanes here, by heavy rain, strong winds, and an eye, a calm region that sits in the middle of the storm, with it worsening on the outside. So with the patterns of how they move, cyclones, they form over warm surface waters. They're driven by energy from evaporation and condensation. That energy in those processes helps to fuel the formation of the storm. Here's one of the things that we want you to know. For a storm to be considered a hurricane, so we're talking in the North Atlantic, in the region, and in the Pacific as well, around North and South America. So in those areas where they're referred to as hurricanes, it must have sustained winds of at least 119 kilometers per hour. I want to make sure that you catch that. That's the equivalent of 74 miles per hour. It does not take 119 miles per hour in order to have a hurricane. At that point, either you're a Cat 3 or Cat 4 by the time you're 119 miles an hour. So it's 119 kilometers per hour, 74 miles per hour. That's in order for it to go from being a tropical storm into a hurricane. We're not going to go into detail with the mechanics here of it, just for the sake of time. I do want you to notice because of the direction of the rotation of the planet, and this is our trade winds are all moving this way because the Earth is speeding this way. We have the Coriolis effect kicking in. All of our storms are they're gonna be moving in that westward direction, and then taking a northward turn in the northern hemisphere, a southern turn in the southern hemisphere. They're going to follow a very predictable pattern, as unpredictable as they can sometimes seem to us, trying to figure out exactly where they're going to hit. Overall, the pattern is very predictable, the type of action that they're going to take. The sustained wind speeds of cyclone can be classified into 5 different categories. You're probably familiar with those categories in terms of our hurricanes that come through. We're probably familiar with the terms Cat 1, Cat 2, Cat 3. Occasionally we see a 4 and 5. Seems like more often we're seeing that. Really, we're seeing more storms than normal, not necessarily an increase in the wind speeds. There could be, at some point in the future, it is possible that a new category could need to be created, that we could get to a point where a Cat 6 is required. But at the moment, we've got categories 1 through 5 for our hurricanes. You can pause this and take a look at those speeds if you want, and break it down. Now we're looking, what happened on that one? All right, go back here. Sorry, I got distracted. All right, impacts of cyclonic storms. So this is our last box now. A couple of the things that we're going to write here. So tropical cyclones cause destruction because of their heavy rains and wind, intense storm surges, and they can also cause tornadoes as well. Something we don't talk about as much with hurricanes, but that maybe we should. Tornadoes can happen in there as well and be major sources of destruction. For us around here, the big talk over the last decade or so has really been storm surges. In our area especially, the storm surges are a pretty big deal, with all the rivers and bodies of water that we have around that can possibly be impacted by those storm surges. All right, so a couple things here that we want you to note. Cyclones move counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. And we're not going to go into detail of the mechanics of that. Just be aware that it's because of the Coriolis effect. And our last slide here, still in impacts of the cyclones, a couple of things that we want you to know. One in particular, the deadliest cyclone on record, was the Bola cyclone, killed between 300,000 and 500,000 people in Bangladesh back in 1970. So in a region that is fairly impoverished and not prepared for a big storm like that, as well as in a time period where the science hadn't quite gotten to where it is now, and our ability to be able to prepare people and evacuate people and try to keep people safe. So just unfortunately a perfect storm in a very bad way that occurred there in 1970. The world's costliest cyclone was Hurricane Katrina. As you can see, not the deadliest, only about 1,000 lives lost. Only 1,000 is still terrible, but when you look at the numbers for the previous one, we feel lucky and fortunate that that we have now the science that we have, and that it hit in a region where buildings are stronger and that kind of thing, where we were a little more prepared, even though New Orleans should have been more prepared than what it actually was. So Katrina was the costliest hurricane. Landfall initially in Miami, and then traveled across the Gulf of Mexico to New Orleans. Was not necessarily expected to hit New Orleans at first, and made a quick little shift right at the end there, which was part of what made it as deadly as it was. So the storm cost between 100 and 200 billion, claimed more than 1,000 lives. We'll be watching a documentary about Katrina in class as well. Just fascinating, but in a truly tragic way, the power that these storms have. So we're going to spend some time the rest of this week talking about these kind of storms. I hope you'll have a good rest of the day. I'll talk to you later. Bye.